All right, so in this lesson, we're going to learn about exact differential equations. In order to do this, we need to take a little bit of information that we learned in Calc 3 and use it as it relates to partial derivatives. So if you need a refresher on partial derivatives, or if you're one of the students who's taking differential equations in Calc 3 at the same time, you're going to have to learn the concept of partial derivatives, and I'll include a link for that in our course. Partial derivatives are not that complicated. It's the same concept of derivatives you learn in Calc 1 and Calc 2. It's just you have multiple variables you're working with, and you have to just know which variable you're working with when it comes time to take the derivative, and all the other variables are treated like constants. So in this case, what we're going to do is we're going to talk about the chain rule and implicit differentiation a little bit. So we look at a function z equals f of xy, and in this function, z equals f of xy, it's a function that has two variables. It's this multivariable function that would relate to a surface in 3D space. And we talked about, taking the derivative of this type of function. And we learned it in the chain rule as it relates to these multivariable functions. One way we can look at taking the derivative of z would be using this formula here. And this is what we call the differential that relates to z. And we saw that in Calc 3 using the chain rule and implicit differentiation. And so that's something we're going to need here in order to talk about exact differential equations. And another way to look at this would simply be, all right, we have this function f of xy, or so z equals f of xy, and we could just use implicit differentiation. So let's say I wanted to take the derivative of f with respect to x for this f of xy. And really, we could just use our basic implicit differentiation we learned in Calc 1. And so, okay, we're going to do this, and this should be the same thing as the derivative of z, with respect to x. Okay, what we're going to need to do is we're going to say, all right, well, if we're taking the derivative with respect to x, we take the derivative of f with respect to x. So we could do that using our partial differentiation, the derivative of f with respect to x. And since, x is the independent variable, the partial derivative of f with respect to x and the standard derivative of f with respect to x, we're basically looking at the same thing here. But anyway, we take the derivative of f with respect to x, and then we could take the derivative of f with respect to y. But since we're doing implicit differentiation, that's where we have to think of y as a function of x and multiply by the derivative of y with respect to x. Okay, so then we have this equation here. We have this dz over dx equals the derivative of f with respect to x plus the derivative of f with respect to y times the derivative of y with respect to x. And then we could just multiply everything through by the dx, okay? And if we multiply everything through by dx, what we see here is that the dx here will cancel. We'll get a dx over here, and the dx here will cancel. And so what you end up with is exactly what we see here, that the derivative of z equals the partial of f with respect to x dx plus the partial of f with respect to y dy. So different ways of thinking about the same thing, but they all related to the same concept. All right, so then let's say we were looking at this function more specifically where the z was a constant, right? So f of xy equals a constant, which if you go back to Calc 3 would relate to the level curves concept. And it's just the idea of if you're looking at a surface in 3D space, you're looking at it from above, and you kind of see the different levels based off of the different constants you would deal with. But either way you do it, it's not really any different. The derivative of f with respect to x, you would get this, okay, differential. So that's what we're getting on this side. But since this is a constant, the derivative of the other side would be 0, regardless of how we're going to do it. A derivative of any constant is always going to give you 0. And so we're looking at this equation, and this is what we're going to use for the concept of an exact differential equation. So here's an example. So here's a differential equation right here. Okay? And this equation has two functions in it, this function and this function on either side, one with the dx, one with the dy. And so if we look at those functions a little bit closer, so if we look at those functions a little bit closer, in relationship to this function right here, okay? So if I call that function, let's say f, it's got two variables in it, so let's say f of xy. And I looked at the partial of f with respect to x, and I looked at the partial of f with respect to y. Okay? So partial derivatives, remember, okay, if we're going to take the derivative of a function with respect to x, and we're going to do that with a partial derivative, x is the variable we're going to be focusing on. So x is our variable that we're taking the derivative with respect to. Any other variable, in this case y, will be treated like a constant. And so either y is going to be a constant multiple, or y is going to be a constant sitting by itself, in which case you apply your basic derivative rules you learned in Calc 1 as follows. So if we're going to take the derivative of f with respect to x, since these are added and subtracted together, we can do each one of these separately. So x squared with respect to x would be 2x. Negative 5xy with respect to x, well, 5 and y are both treated like constants. So they're both constant multiples, so the derivative of x with respect to x is 1. So then we leave the constant multiples there. We get minus 5y. And then we take the derivative of y cubed with respect to x. That's a constant because y is a constant. So y cubed is a constant. That would just give me 0. Then we do the same thing again with y. Y is our variable, so x is treated like a constant. So x squared would then be 0 because x is a constant. Negative 5xy would be minus 5x this time because the 5 and the x are constants, but y is my variable. And then the y cubed would be 3y squared. And then I look at that in respect to what I have here. Well, look at this. This is exactly this function, and this is exactly this function, which tells me that if I call this f, this is the partial of f with respect to x dx, and this is the partial of f with respect to y dy, and if this side is 0, okay, then that means that I took the derivative of some constant. So if I asked you, what's the solution to this differential equation, I'm asking you what function satisfies this, or what function did we take the derivative of to get this equation, in which case this is it. We took the derivative of this side, and we got this, the left-hand side, and on the right-hand side, it had to be a constant, and that's why we got 0. So the solution to this differential equation would be this function right here. And another way of looking at this differential equation would have been to stack up our dy dx's, so move some things around. We would have gotten this, and this takes us back to our implicit differentiation concept we learned in Calc 3, where we said, okay, we have this formula, negative fx over fy, as our implicit differentiation formula for Calc 3. That's exactly what you're seeing here, the partial with respect to x, the partial with respect to y, with that added negative to it, but nonetheless, there's what we got. So what we're looking at here is this formula for finding the solution to a differential equation. And this is all well and good because we had this function sitting in front of us with this differential equation. We kind of saw the relationship between them. It's not always going to be that simple. Most of the time, all the time, we're going to have this differential equation. We're going to have to come up with this function. But you see the relationship is the point. And the relationship follows through this, what we're going to call an exact differential. Okay, so here now we have our definition we're going to use for exact differentials and then therefore exact differential equations. So let's look at first exact differentials. So let's say we have a setup where we have this function m, which is a function of x and y dx, and then n, which is another function of x and y dy. So let's look at something in this form. This would be considered an exact differential, okay, if it corresponds to the differential of a function. So therefore, this right here, m is the partial, m is the partial of some function f with respect to x, and n is the partial of that same function with respect to y, then this would be considered an exact differential. Just going back to the exact same thing we talked about a minute ago. And if we take that differential and set it equal to 0, then we get an exact differential equation. So if I looked at an equation like this equation is an exact differential equation because this function here, x squared y cubed, is the derivative of some function, specifically this one, with respect to x. So if I look at, say, f, and I call f 1/3 x cubed y cubed, and I look at the partial of f with respect to x, well, that's going to give me x squared y cubed because the 3 would come out and cancel to 1/3. And I look at the partial of f with respect to y, and that's going to give me x cubed y squared. So if I look at these two pieces here for this function. This is the partial of some function with respect to y, and this m is the partial of that same function with respect to x. If this side fits that setup, then the left-hand side is an exact differential, and since I then set it equal to 0, the right-hand side is an exact different. The right-hand side is 0. This whole thing is an exact differential equation. And then what's the solution? Well, the solution should be that function equals c. C because of the right-hand side being 0. And so the solution to that differential equation should be 1/3 x cubed y cubed equals c. Okay? And that's all well and good, again, because this was sitting in front of us. But how are we going to know that? How am I going to look at a differential equation and know that it fits that criteria of two different partial derivatives of the same function on the left-hand side so that I have an exact differential? Well, this is how we're going to do it. We're going to look at the left-hand side, this m and n function, and we're going to say, well, this is going to be an exact differential if the partial of m with respect to y equals the partial of n with respect to x. Now, why are we going to do this? Again, goes back to Calc 3. So in Calc 3, we talked about something called a mixed partial derivative. So we looked at the derivative of f with respect to x, and then looked at that same function and now took the derivative with respect to y, which was one of our second derivatives, and we called it a mixed partial derivative. So x first, and then y second. And then we looked at the derivative of that function f, and we took the derivative of y first, and then x second. And what we saw was that these should be equal to each other as long as the function is continuous. And so that's where we're talking about. We're talking about continuous functions, continuous first partial derivatives on some region. That's where all this piece and the criteria comes into play. But how does that relate to here? Well, remember, m, we're hoping, is already the derivative of some function with respect to x. And n is already the derivative of that same function with respect to y. So then if I take the derivative of m with respect to y, which would be the same thing as taking the derivative of f with respect to fx with respect to y, I would have this mixed partial. And if I take the derivative of n with respect to x, that would be the same thing as taking the derivative of this with respect to x, and I would give me this mixed partial. And the idea is if these two things are equal to each other, then in fact, m had to be the derivative of f with respect to x, and n had to be the derivative with respect to y. So follow it backwards, it would have said, well, then this had to have happened. So that's how we're going to check to see if we have an exact differential equation, by doing these two partial derivatives. M being the function in front of the dx, n being the function in front of the dy. All right, so the way now we're going to solve this differential equation, this exact differential equation, there's two ways to do it. This first way is the way you're going to see done most often in a textbook, and even lots of times in lecture videos you'll find online. This is the more standard way of doing it. It's also the longer way of doing it. We will have quicker ways, and I have a quicker way we can look at to get this done that I like a lot better. And it does relate to something we would have seen, again, in Calc 3 as it relates to some of the vector spaces that we would have talked about. So nonetheless, and vector fields, sorry. And nonetheless, though, we'll go through this long way first. Again, this is the standard way of doing it. And then I'll go ahead and show you the quicker way to go. So first, let's look at this equation here, and let's say, all right, we want to solve this differential equation. First thing we want to do is we want to check to see, is it an exact differential? All right, so if it's an exact differential, first off on the left-hand side, all right, then we'll move forward. But that's the first thing you have to check. So we're going to see, does the partial of m with respect to y equal the partial of n with respect to x? And if so, all right, we have an exact differential. So then that's telling me that I know that the derivative of f with respect to x is this m function. And ultimately, what am I looking for? I'm looking for that function f. And my answer will be f of xy equals c. So I'm trying to now go back and build this function f, knowing that m is already the derivative of that function with respect to x. Well, if m is the derivative of that function with respect to x, then I should go back to f by taking the integral with respect to x. So if I want to do this, what I'm going to do is I'm going to take the integral of m with respect to x to try and get back to f. In doing so, what am I going to do? Well, I have two variables here, and I'm integrating only with respect to one of them. So I'll integrate m with respect to x. Okay? So you do that the same way you do the derivative with respect to x. X is your variable, y is treated like a constant. Well, this isn't this integral right here is an integral where we have an indefinite integral. And so when you have an indefinite integral, you usually have a plus c after you integrate. Well, this right here is our plus c. Why? It's not as plus c, right? You see it says g of y, not plus c. Well, the reason why it says g of y is because, remember, y is treated like a constant when we do this integration. And if y is treated like a constant when we do this integration, then the constant should be anything we treated like a constant, which could be a function of y. So the idea here is this is our plus c for this indefinite integral. So when I go ahead and do this, this is what f of xy should equal. All right, well, that's well and good. That's what I'm looking for. The problem is I don't know what this g of y actually is. I just know it's a function of y. So that's the constant I'm trying to find. So now the rest of this problem is to just finish this off to try and figure out what that other piece is. And once we do that, now we can find the function f of xy. So the next thing we're going to do, okay, is to say, well, we know that n, that other piece to this differential equation, n is the partial of f with respect to y. Okay? All right, well, if this is what f equals, if this thing right here is what f equals, if I take the derivative of f with respect to y, okay, then I should take the derivative of this with respect to y. So I'm going to take the derivative of this piece with respect to y. And what am I going to do? I'm going to take the derivative of the integral with respect to y, which this integral is just some function, right? Depending on what that integral ends up being, it's going to be some function. We're going to take the integral of that with respect to y. And then I have to integrate this other piece with respect to y as well. Well, since it's just a function of y, it would just be the derivative of g with respect to y, so g prime of y. And that should be equal to n, because n was also the derivative of f with respect to y. So this equals n. All right, so I have this equation right here. What I'm going to do is I'm going to solve this equation for g prime. So I'm going to move this to the other side of the equation with the n. So I subtract it. That's what you see here, right? And so g prime of y equals n of xy minus the partial of this integral with respect to y. Well, I don't really care what g prime of y equals. What I ultimately want is what g of y equals, because then I can fill it in here and I know my f. So again, first step we got here, and we had almost the answer we were looking for. We had the f, but we were missing this one part. So now the rest of this is saying, well, if I know what g prime of y equals, in order to figure out what g of y equals, I just need to integrate it. And that'll give me gy. Well, if I integrate this, I should integrate this piece. So finally, what are we going to do here? What we're going to do is we're going to integrate that piece. Okay, that's going to give me my g of y. Once I figure out what my g of y is, I fill it in up here, and then we have our solution. So looking at this, we can realize that this is a way that we can go back and build up our function f of xy. But once we build the function f of xy, the solution isn't f of xy, but remember, instead it's f of xy equals c because of the right-hand side. So once we do that, we have our solution. And so understanding that this is how we're going to get this done is is one way of looking at this. I think this tends to be confusing for some people because you're saying, well, what am I integrating with respect to at what step? What variable am I working with? What function am I working with? But this is one way to do it. And like I said, this is probably the more standard way you see it done. This is actually not the way necessarily that I would do these problems if I was working with them myself. So if I was going to work with these problems myself, what I would instead do is talk about something we did back in Calc 3 when we talked about conservative vector fields. This all relates to the concept of a conservative vector field, because a conservative vector field is a vector field that is made up of partial derivatives of a function. And then we talked about the potential function. The potential function is that function that we took the derivative to get the conservative vector field. And hopefully you remember this. If not, we're going to have to go back and review that on your own time. But this concept of conservative vector fields is the same thing. So again, what do we have? We had in Calc 3, we had this function f of xy. And if I took the derivative of this function with respect to x, and I took the derivative of this function with respect to y, and I created a vector field with this. So this conservative vector field, right, which we also called the gradient, where the components of the vector field were these partial derivatives, okay? And we looked at a vector field that was made up like this. And what we were asked to do is say, okay, one, how do we know this is a conservative vector field? And we had this concept of cross partials, which is the same concept of checking to see if a differential equation is an exact differential equation. And we were asked to say, okay, then go back and find that potential function, the function that gave you this vector field. So you would have to find the function that you took the derivative of with respect to x and also with respect to y to get these two components and rebuild that function. Well, that's exactly what we're being asked to do here. And so the way we did it is we said, okay, well, let's integrate this piece right here with respect to x, and let's integrate this piece here with respect to y, and they should both give me the same thing. They should both give me that function that I'm looking for. So let's set them equal to each other in order to build that function up. So if I do that here with this exact differential equation, and I go, okay, I have this function mxy dx plus nxy dy equals 0, and I check and I know that this side is an exact differential, meaning that I know that this is the partial of some function with respect to x, and I know that this is the partial of that exact same function with respect to y, and I'm trying to find that function. Well, what I should do is I should integrate m with respect to x, and I should integrate n with respect to y, and both of them should get me that function that I'm looking for, f. Well, if they're both going to give me f, then they should equal each other, and that should get me back to this function f. This is a much more straightforward way of getting to that function f than what I showed you a second ago. But this requires two integrals. And in the long run, it's easier to differentiate than it is to integrate. So the reason why that method I had a second ago is the more standard way of doing it is it requires you to do one integral. We do this integral to start with, and then we switch over to taking the derivative in order to match up with this function here. Well, these functions right now are going to be fairly simple anyway. There's two variable functions, so doing two integrals shouldn't be all that complicated. So we match these two integrals up. Once we match these two integrals up, we find out how to build the function f from those two integrals. And then finally, we say, all right, well, then the solution to the differential equation is not just f of xy, but should be f of xy equals c, again, because of the right-hand side being 0. We're finding the function for the left-hand side, and then the solution to the differential equation should be c because of the right-hand side. So this is the more straightforward way to do it. This is the way I will do most of these. Now, I'll show you the first example in both formats, but for the most part, we're going to follow this one. And if you want to refresh your memory on some of this stuff, go back and look at conservative vector fields, potential function, and then also the fundamental theorem for conservative vector fields, which is a way of integrating those vector fields, which is ultimately what we're relating this all to. Okay, so here's an example. solve this differential equation. First off, we have to decide what kind of differential equation is it. Okay. Well, let's look at the 2xy, and let's look at the x squared minus 1. Let's call this one m, let's call this one n. And let's look at what the partial of m with respect to y is. Okay. And ultimately, what we want is to think of m as with respect to x, but to check it, we do the m with respect to y. Remember, what we're really doing is this mixed partial derivative equality. So if I take the derivative of m with respect to y, x is treated like a constant, and therefore I would get 2x, because the 2 and the x are essentially treated the same way. And the derivative of y with respect to y would be 1. And then I'm going to look at the derivative of n with respect to x, in which case I'm going to get 2x. For all the same reasons you do your standard derivative. X is the variable. There are no y's in that one, so this is just basic Calc 1 derivative. And you get 2x. Notice that they are equal to each other. So that tells me that this right here is an exact differential equation. All right. So then what we're going to do is to solve the differential equation. That was just a check. Okay, that was just our check. To solve the differential equation, what we're saying is that, well, what we just showed is that m is actually the derivative of some function with respect to x, and n is the derivative of that exact same function with respect to y. That's what this just checked out. So now we got to find that function. So what I'm going to do is I'm going to integrate m with respect to x. And that's going to give me the integral of 2xy with respect to x. In which case, you integrate with respect to x the same way you differentiate with respect to x. Y is treated like a constant. So this would give me x squared y. But we should have a plus c because this is an indefinite integral. But since y was treated like a constant, then the constant for this integral could have y's in it. So we'll call this a function of y. That's our constant of integration. Then we're going to integrate n with respect to y. So that would be the integral of x squared minus 1 with respect to y. And if we integrate this with respect to y, notice that none of this has any y's in it. So this whole thing is just one giant constant. So if it's one giant constant, we should have x squared minus 1 y plus a c. In this case, our c would be a function of x. But the idea is that this should equal f and this should equal f. So therefore, they should equal each other. Well, if x squared y plus g of y has to equal x squared minus 1 y plus h of x, we can use this to help us figure out what f should be. So we have x squared y plus g of y. Here, if I distribute this y in, I have x squared y minus y plus h of x. Noticing that we have an x squared y on either side, that tells me the remaining pieces, this and this, have to equal each other. Well, the only way a function of y, g of y, could equal this minus y plus h of x, remember that g of y means that this only has y's in it. And if it's equal to this, well, there's a y, but this says this has x's in it. Well, this can't have x's in it in order for this to work out, that this is equal to this function of y. So it tells me that g of y has to equal this minus y. Putting that in here, remembering that both of these are f of xy, that tells me that f of xy has to then equal x squared y minus y. And if you want to double check that, now go back and take the derivative of this with respect to x. You'll see you're going to get m. Take the derivative of that same thing with respect to y. You see you're going to get n. And therefore, the solution should then be that equals c. Mixing in this right-hand side of 0 into the whole process, there's your solution to your differential equation. If we wanted to take the other approach, like I said, the more standard approach, we really would start it the same way. We would check to see if this is an exact differential. So we're going to assume it is already. We've already checked it. We're going to start off by saying, okay, let's take the integral of m with respect to x, and we're going to do that. And so with the integral of this 2xy with respect to x would give me this x squared y plus g of y. And we're going to say, okay, well, that should equal f. Rather than switching over now to this other integral, what we're going to say is, well, if that has the equal f, then as long as I can find g of y, I'm done, right? I mean, I have my f that I was looking for. So we switch now to doing it by derivative. So we do it by saying, well, if this is supposed to be the derivative of f with respect to y, and this is f itself, let's take the derivative of this with respect to y. Let's take the derivative with respect to y of x squared y plus g of y. In which case, since these are added, we'll do each one of these separately. We're going to get x squared plus g prime of y. So that's this piece right here. Okay, so if we do that, right, we would get this as our answer. Now that should be the same thing as what's sitting right here. So that should equal n, which is this x squared minus 1. If you match those two up, here's your x squareds, boom, there's your minus 1. So that tells me that g prime of y equals negative 1. Well, if g prime of y equals negative 1, I really don't care for that so much as what I care for is what g of y equals. Well, if I integrate g prime of y, that should give me g of y. And so therefore it should be the integral of negative 1 with respect to y. Again, the variable here is y, which should be minus y. You could say plus c, but we're going to throw the plus c at the end anyway, so we're going to leave that off for right now. Well, if g of y is negative y, and we throw that in there, what do we got? We have x squared y minus y is our f of xy. So again, same thing we got a second ago, just slightly different method by turning to derivatives instead of straight integrating twice. But nonetheless, our solution would then be x squared y minus y equals c, throwing that c into the process. And you see, that's where the constant would have came in if we said, okay, plus c there. It's the same idea. We just would have lumped it all on the other side of the equation. But we get the same solution with a slightly different method. I think this method tends to be a little more cumbersome than necessary. I do find students confusing when they take the derivative, when they take the integral, what variable they're working with, and the other method a little more straightforward, but you choose what works best for you. Okay, so then now what we have is this differential equation that we want to solve. So first, we have to decide what kind of differential equation it is. And at this point, we have a couple we could choose from: separable, homogeneous, exact. And so we're going to have to get better at deciding that. I think right away you can see it's not separable. There's no way I'm separating these variables. Homogeneous, I think you can throw off right away. So then let's check exact. So we got to look at this, call this one m. That's the one in front of the dx. Look at this one here. We'll call this n. Okay. And let's look at the partial of m with respect to y. And so the partial of m with respect to y is my variable, x is my constant, in which case I'm going to get 2e to the 2y minus, I'm going to have to use product rule to take the derivative of this thing with respect to y. So I'm going to get 1 times cosine of xy. Then I'm going to take the derivative of the other part, so I'll have this minus y. Now the cosine's derivative with respect to y, so the derivative of cosine would give me minus sine, so I'll add it to a plus. Inside stays the same, xy, no comma there, xy. Then I multiply by the derivative of the inside with respect to y, which would just give me x. So we're talking chain rule here, we're talking product rule here, but anyway, that's your derivative with respect to y. Then we're going to go derivative with respect to x for n, and if we get the same thing, we have an exact differential equation. So derivative of this thing with respect to x would just give me 2e to the 2y, because x is the variable, everything else is a constant. Take the derivative of this with respect to x, we're going to need product rule again. So I'm going to have minus 1 times cosine xy. That's the first part of the derivative. That's the derivative of the first component. Then we go to the second one. Then we got to take the derivative of cosine. In doing so with respect to x, I'm going to have this minus x still here. So now I need the chain rule to take the derivative of the cosine. So derivative of cosine is minus sine. So I'll put that as a plus. Then I have to take the derivative of the inside with respect to x, which would give me y. And then this third piece with respect to x would just give me 0. Well, taking a look at these two functions, they are the exact same thing. I mean, these two functions are the same. Since they equal each other, this is an exact differential equation. All right, now that it's an exact differential equation, what are we going to do? We're going to go ahead and solve it and find the function that satisfies this equation. So in doing so, what I'm going to do is I'm going to take the integral now of m with respect to x. So that's the integral of e to the 2y minus y cosine xy with respect to x. And that's going to give me x e to the 2y, because e to the 2y is really just a constant in terms of x. So it'll be x times the constant, minus, again, with respect to x, this y is a constant multiple. I'll pull it out. So I'm really just taking the integral of cosine xy with respect to x, which would give me sine xy over y, plus my c, which would be some function of y, because I treated y like it was a constant. Well, these two y's will cancel, so this is where we're at. All right, then we go the integral of n with respect to y. So if we did the integral of n with respect to y, what I'm going to end up with here is the integral of this with respect to y. So this whole thing is just one giant constant multiple. So we have this 2x. Let me just write it all down first. 2x e to the 2y minus x cosine xy plus 2y, again with respect to y. So what we're going to end up with here is going to be an x e to the 2y for that first piece, because the 2's will cancel. When you integrate e to the 2y with respect to y, you divide by 2. Then we're going to have this x as a constant multiple, so we're really just taking the integral of cosine xy, which will give me sine xy, this time divided by x, which is the constant. And then we have the 2y, which would give me y squared with respect to y, plus c. But c here could be a function of x, so we have plus h of x. So now what we're going to do is we're going to see, okay, these two x's cancel here and here. We're going to match these two things up, because remember, this should equal f, and this should equal f. Well, seeing that these are exactly the same, these are exactly the same, then these two have to equal. So this tells me that g of y has to equal y squared plus h of x. Well, the only way those two things could equal each other is if g of y equals y squared and h of x is 0 or constant at best. Okay? So then filling that in, my solution, my function, remember this is equal to f, my function should be x e to the 2y minus sine xy plus g of y, which is y squared. And the solution to the differential equation should be when that equals c. And so there's the solution to differential equation using exact differential. All right, let's try this one out. Now, we got to set this one up a little differently first to decide what kind of differential equation we have. It's clearly not separable. I'm not going to be able to separate these variables out. And homogeneous is not an option here either. But we also have to rewrite it so that we can write it in terms of an exact differential equation, get our m and n functions. So I'll cross multiply here. I'll move everything to one side so it's set equal to 0. In the end, we have this initial value component, which is just something we'll do after we solve it. But first, we'll solve the differential equation. So what we're going to end up with here is xy squared minus cosine x sine x dx minus y times 1 minus x squared dy equals 0. Now it's minus because I have to move it over to the other side of the equation. And I mean, I could have moved the dx component over or the dy component over, but I chose the dy, so that's a minus in front of it. So then here's our m is right here. And with the negative attached to it, this is my n. So first we got to decide, is it exact? So let's see, does my equal nx. Okay, the derivative of n with respect to y equal derivative of n with respect to x. So in order to do that, what we're going to have to do is say, all right, well, let's take the derivative with respect to y here. So that's going to be pretty easy. Y is the variable, x is the constant. So we're going to get 2xy, and this is going to be 0. And n with respect to x, well, if you look at n with respect to x, this is a constant multiple. So we have minus y times the derivative of this thing with respect to x. Well, that with respect to x will be minus 2x, which gives me 2xy. And so, yeah, in fact, this works out. So we do have an exact differential equation. All right, so now we got to go about solving it. So if we integrate m with respect to x, so that's xy squared minus cosine x sine x. We do this with respect to x now. So x is the variable, so I'm going to get x squared y squared over 2 minus, if I do this with respect to x, I'm going to have to use u substitution. We'll call sine x my u, and cosine x, the x would be my du. So if it's a u du, then I should get u squared over 2 as my integral. So this should give me sine squared x over 2 plus c, which could be a function of y. And then I'm going to do the same thing with the n, but this time with respect to y. So I have minus y times 1 minus x squared dy. If you want to distribute this in or leave it out, that's up to you. Since we're integrating with respect to y, this whole thing is just one giant constant. So it's just as simple saying, well, the integral of y would be y squared over 2. So minus y squared over 2 times this constant multiple plus this function that is my constant, which could have x's in it. So it's function of x. And then we say, okay, well, this should have equaled f, as well as this should have equaled f. They both should go back to the same f, since it's exact, okay? So we go and match these things up here. Well, we would distribute this in here and here, okay? And what you're going to see is that this is going to give me minus y squared over 2 plus x squared y squared over 2 plus h of x. And so these are the same. So that tells me that the remaining pieces, which is this minus sine squared x over 2 plus g of y, has to equal this minus y squared over 2 plus h of x. Well, this g of y has to be this function of y. This h of x has to be this function of x. So you match them up. You either fill in the h of x here or you fill in the g of y here. We just figure out what each of those are. And our solution would be that function f equals c. So what is f? F would be x squared y squared over 2 minus sine squared x over 2 plus g of y, which we said was going to be minus y squared over 2, and that should equal c. If I use this other one, it's really the same exact function. I would just fill in minus sine squared x over 2 and for h of x. Either way, maybe it looks a little different because of the way this is written here, but it's still the same function, remember. Just distribute it, just factor it out with the y squared. But nonetheless, there's your solution to your differential equation. Okay, so if we then solve the associated initial value problem, well, we had the solution of x squared y squared over 2 plus sine squared x over 2 minus y squared over 2 equals c. And the initial value problem of y of 0 equals 2. I could leave it like that and I can go ahead. I could have simplified the answer a little bit more. I could have multiplied everything through by 2 and got x squared y squared plus sine squared minus y squared equals 2 times c, which I could still just call c. But now remember, this c is different than that c. So if I then go solve the initial value problem and I try and solve for c, whether I use this one or this one, I'll get a different c answer, but not get a different answer overall for the equation. And let's just look at it to make some sense of that. So this would be x, this would be y. If I plug them into this equation here, I'm going to get 0 for x is 2 for y, so 0 times 4 plus sine of 0 is 0 squared minus 2 squared equals c. So you see you get c to be negative 4, okay? As opposed to if I plugged it in here. Well, if I plug it in there, I'm going to get 0 times 4 over 2 plus 0 squared over 2 minus 4 over 2 equals c. And you see what you end up with is that c equals negative 2. Now, even though it looks like I got two different c's here, depending on which equation I used, I really have the same equation because either I got x squared y squared over 2 plus sine squared over 2 minus y squared over 2 equals negative 2, or I got x squared y squared plus sine squared minus y squared equals negative 4. Okay? In which case, they're really the same equation, because if I take this equation, I get rid of the 2's, I multiply by 2, I get this equation. Yeah, it looks like two different c's, but it's still the same solution. That's why it doesn't really matter whether you multiply the 2 through and leave it embedded inside the c and then just call the whole thing c. It ends up in the same answer either way. So what this one probably looks the best. So we would say that x squared y squared plus sine squared x minus y squared equals negative 4 solves the IVP. Okay, so now that we have this concept of how we're going to solve differential equations, exact differential equations using this method, we look at this next thing called exact differentials. Now, integrating factors. Let's track back a couple of seconds. Integrating factors. This is going to be really important when we go to the next step, which is solving linear first order differential equations, which will then lead us really into the whole semester, which is we're going to solve linear differential equations pretty much for, 3/4 of the semester. But anyway, let's assume we have a differential equation like this. mxy dx plus nxy dy equals 0. And let's say that this is not an exact differential equation. Okay, we checked it. The partial derivatives don't work out. The derivative of m with respect to y doesn't equal the derivative of n with respect to x. So it's not an exact differential equation. And therefore, we can't do what we just got done doing with all those examples. But let's say, what if there was this function mu that we're going to call an integrating factor such that if we multiplied it through the equation, so we multiply this entire equation through by mu, so m gets multiplied by mu, n gets multiplied by mu, and the other side gets multiplied by mu, but that still would stay 0. Let's say there's this function mu that if we did multiply the equation through by mu, we could create an exact differential equation. Now this whole piece here is in front of the dx, and this whole piece is in front of the dy, and those partial derivatives work out to be exact. Okay. Well, then once we do that, now we have a way of solving this thing using the same methods we just talked about. So is it possible for this to happen? Okay. If so, we need to figure out how we're going to find this random function mu. And then, is it possible for us to get a solution by doing this? Okay. So that's where this integrating factor concept comes in, is can we come up with a function mu that would turn this into an exact differential equation and therefore make it solvable using the exact methods? Well, the answer to that is simply yes. Now, that's, a little too simplified. Sometimes yes is really what it should say. Okay. So here's the example. We're not going to go through and actually solve this thing all the way out. We're just going to check to see if this concept in fact works out, because once we decide that we can turn it into exact, we could solve it using the methods we talked about. So first, look at the original differential equation here. Here's m, here's n, okay, n and m, okay? And so what we're going to do is we're going to say, all right, well, let's look at the derivative of n with respect to y. What are we going to get? Well, with respect to y, this will be 0 and this will be 1, okay? And then let's look at the derivative of n with respect to x. Well, this with respect to x, we're going to need to use the product rule. So the derivative of x with respect to x is 1, so we just have log x, plus x times the derivative of log x with respect to x would be 1 over x. So ultimately, this would simplify to be 1, so we'd have log x plus 1. And so clearly, they are not equal to each other. My does not equal nx. So this is not exact. All right, but what if I multiplied everything through by 1 over x? So if I multiplied everything through by 1 over x, what's going to happen here? Well, what's going to happen is, I look at m now would be 1 over x times x plus y. That would be my new m, and my n would be 1 over x times x ln of x, which ultimately would just be ln of x. And then I looked at the partial of this one with respect to y, and the partial of this one with respect to x. And what am I going to get? Well, with respect to y, this is a constant multiple, so that's going to come out. And this with respect to y is still going to be 1, so I'll get 1 over x times 1. And this with respect to x is going to be 1 over x. And what I get is that these things do equal each other. So now, with this as my new m and this is my new n, I do have an exact differential equation. If I multiply through by 1 over x, I can turn something that's not an exact differential equation into something that is. And the second I do that, now I'm going to be solving this differential equation. 1 over x times x plus y dx plus 1 over x times x ln of x dy equals 0. And now I'm going to solve that differential equation using the methods of exact. So here's just an example. But this isn't always going to work. So the question is, okay, well, when is this going to work out? That I can find some function mu, that integrating factor. And how do I find the function? So the way we're going to do this, and we have to simplify it a little bit, but the hard part for finding mu is to come up with a way of doing it. But what we're going to do here is we're going to say, let's think about this, right? Remember, the criteria was that the derivative of mu times m with respect to y has to equal the derivative of mu times n with respect to x. And we're trying to figure out when is that going to happen and what would mu have to be so that those are equal. Well, if we looked at each of these derivatives here and we used the product rule because we have mu times n, and then we rearranged our terms, we would get to this equation here. If we look at these three different, or let's say, 4 different pieces here, we have m, we have n, we have my, we have nx, and we solve for mu. Well, we would have to make an assumption, right? The assumption would have to be that either mu is a function of x or a function of y. It's a single variable function for us to be able to do this. Otherwise, there's too many variables here to assume here. So if we did this, we could break things down into 2 cases. One, if my minus nx over n is a 1 variable function, specifically a function of x alone, then we could solve for mu here by using this formula, okay? And we would have to do a little bit of manipulation of the equation. We would have logarithms, in which case we'd have to exponentiate, and we would get this function mu to look like this: e to the integral of my minus nx over n dx. And that's only if this is a function of x alone. So can we find mu? Yes, if we make these stipulations. The other option is that this nx minus my over m, so we're basically just solving this kind of in a reverse order, and that ends up being a function of y alone. Well, if that's a function of y alone, then mu should be a function of y. Again, just sort of simplifying this a little bit and solving for mu, we would get this formula here. And so if these things happen, then we should be able to find an integrating factor, mu, either mu of x or mu of y. But once we have that mu, we can multiply by that integrating factor, and we could solve the differential equation using the exact differential methods. So let's look at this one here. First, here's m, here's n. This is not exact. My, which would just be x, does not equal nx, which would be 4x plus 0 plus 0. So clearly they're not equal to each other. However, if I look at these things and I do a couple of different derivatives, so I have m, which is xy. I have n, which is 2x squared plus 3y minus 20. And then I look at partial derivatives, so mx and my, my and nx, okay, which we already have, x and 4x. And then I look at that formula. So this would be the formula where we're looking at my minus nx all over n. Okay. And what you see here is that my would be x minus nx, which would be 4x, all over n, which would be 2x squared plus 3y minus 20. That is not a function of x alone. Okay. So then let's look at the other one, which would be nx minus my over m. So it's just reversing the order here. So we have 4x minus x over, in this case now, xy. Well, now I get 3x over xy. The x's cancel. I get 3y. That is a function of y. Okay? So that tells me if I use that second concept, I should be able to find the integrating factor. And the integrating factor should be e to the integral of this, which was this 3 over y, dy, and I would get e to the 3 ln of y, which would then give me, bring the 3 in, e to the ln of y cubed, which would give me y cubed as my integrating factor. So this tells me if I multiply these by that integrating factor, it should then turn into an exact differential equation. Well, let's see if that happens. All right, so if we look at the differential equation again, xy dx plus 2x squared plus 3y squared minus 20 dy equals 0. And we multiply through by y cubed, that would give us xy to the 4th dx, plus I'll just say y cubed times 2x squared plus 3y squared minus 20 dy equals 0. And now here's my m and here's my n. So now I look at my, and I'm going to get 4xy cubed. And I look at nx. Well, the y cubed is a constant multiple, so then I'm going to get 4x plus 0 plus 0 with respect to x, which is ultimately 4xy cubed, these are equal. So now this is exact by using that formula we came up with and our y cubed being our integrating factor, which we would then go ahead and solve this differential equation using our methods before. And so it is possible, but there's a lot of stipulation here. We have to look at those two formulas. We have to either get a function of x only or a function of y only. In the long run, we're not going to use that as much, but the concept of an integrating factor will come into play when we talk about linear differential equations, and we'll have to find the linear integrating factor that we're going to work with using similar methods. So you'll see how this all connects next lesson.